is 周佑宸, and we begin with a 3.1 representation code, a basic form of error correction. By repeating each bit 3 times, we can correctly interpret the intended value even if a single bit error occurs during transmission. Beyond simple representation, we look at more efficient error correcting codes by ensuring any two patterns are separated by a Hamming distance of at least 3. We can distinguish symbols more reliably. The minimum Hamming distance d-min is crucial as it determines a code's error detecting and error correcting capability. To detect the k errors, the code must have a Hamming distance of at least k plus 1. For error correction, the requirements are structured. A Hamming distance of 2k plus 1 is required to correct k errors. This distance is achieved by adding a suitable number of parity bits to the original data word. Let's define our variables. N-bit code words consist of m data bits and r redundant parity bits, where n plus r. To correct a single bit error, we must be able to identify which of the n positions is corrupted. With n bits, there are 2 possible patterns, but only 2 other n's are varied. This leads to the inequality like this, and this formula establishes the lower limit for the number of check bits required. For a 4-bit data word, the inequality these ones. And implies r must be at least 3. Thus, we add 3 check bits to correct single bit errors in 4-bit data. For an 8-bit data word, and this one, implies r must be at least 4. This results in a 12-bit code word. The real challenge is determining how to assign values to these check bits. With 12-bit code words, we observe that each bit's position can be expressed in powers of 2. For instance, 1 is this, like this one, this picture. This mathematical structure is the key to creating our check bits. Following this, each bit position corresponding to a power of 2 is reserved for a check bit. This check bit stores the parity of all bit positions that participated in their specific summation group. Bit 1 checks parity over positions 1, 3, 5, 7, and 9. Bit 2 checks positions 2, 3, 6, 7, 10, and 11. For the word 1101, 0110, we calculate the parity values for the check bits. The completed code word ensures even parity within each group. Bit 4 checks positions 5, 6, 7, and 12, while bit 8 checks 9, 10, 11, and 12. Using this algorithm, we can detect and correct any single bit error. If an error occurs at bit 5, we check the parity. Bit 1 and bit 4 will show an incorrect status as they no longer maintain even parity. This clearly indicates a problem in the data stream. And finally, we find the error by adding the positions of the erroneous parity bits. Since 1 plus 4 equals 5, we know the error is at bit 5.